This is a continuation of section 1.1 exponential notation for math grade 8. We're going to start on page 8 now, doing the section that starts with use exponents to write the prime factorization of a number. In this section it says any composite number can be written as a product of prime numbers. This prime factorization of a number can be expressed using exponents. If you want to use the following divisibility rules to help you find the prime factors. Divisibility rules. A number is divisible by 2 if the last digit is even. For example, 0, 2, 4, or 6. Or 8. Like 10 ends in 0, therefore it can be divisible by 2. 66 ends in 0, therefore it's divisible by 2. It's divisible by 3 if the sum is divisible by 3. For example, 33 can be added together to make 3 plus 3, which equals 6. 6 is divisible by 3, therefore 33 is also divisible by 3. It's divisible by 5 if the last digit is 0 or 5, which makes sense considering that when we count by 5s, we either get to a 5 or a 10, and then 15, 20, 25, 30, and so on. It's divisible by 7 if the last digit, when doubled, and subtracted from the number formed by remaining digits gives a result of 0 or number divisible by 7. For example, 42, we take the last digit, we double it to make 4, and subtract this digit from this digit, which is 4 minus 4 equals 0. And that means 42 is divisible by 7. Now let's try example number 5. A. Write prime factorization of each number in an exponential notation. Let's start with 81. 81 equals 3 times 27 equals 3 times 3 times 9 equals 3 times 3 times 3. Now, how we got here? We found that 81 is divisible by 3 because 8 plus 1 is 9, that's divisible by 3. 27, you add those together, 2 plus 7 is 9, that's divisible by 3. We know 9 is divisible by 3 to give us 3 to the 4th power. 3 is our repeating number, repeated 4 times. That gives us our exponent. Now simplify, and that gives us this. Okay, let's try this another time with 1,125. The last digit is 5, so we'll start by dividing it by 5. The last digit again is 5, so we'll divide it by 5 again. The last digit's 5, we'll divide it by 5 again. 5 is an easy number to keep dividing by. Now 9 does not end in 0 or 5, however we know that it's divisible by 3. Simplifying, we get 5 cubed because 5 occurs 3 times, times 3 squared because it occurs 2 times. Let's try C. 1,470 divisible by 5 because the last digit is a 0 equals 5 times 294. 294, the last digit is even, we'll divide it by 2. $147 is divisible by 3 because 1 plus 4 is 5, plus 7 is 12. That's divisible by 3, so the whole number is divisible by 3. 49, you add those together, gives you, 49 is divisible by 7, I apologize. 49 is divisible by 7 because the last number taken times 2 is 18. 18 minus 4 is 14, and that is divisible by 7. Therefore, it is divisible by 7. You have to pull out all your tricks. And then we get 2 times 3 times 5 times 7 squared. That's example number 5. Go ahead and do guided practice on page 10, problems 11 and 12. Now let's try example number 6. In example number 6, we will start with A. A says there are 20 bacteria in a given sample in a laboratory. During the early phase of culture growth, the number of bacteria keeps doubling every hour. How many bacteria are there after 3 hours? Write your answer in exponential notation. So let's try this. There are 20 bacteria in any given sample in a laboratory. So we draw the original. This is representative of 20. Now, after 1 hour, we double. That gives us 2. So we have 20 times 2 amount of this little bacteria here. After 2 hours, it is again doubled, giving us 4. 20 times 4. Each of these is representative of 4. We doubled. If we go after 3 hours, how many will we have? So, the initial number of bacteria times the rate of growth over 3 hours. Can't forget to substitute this one, or it will become more confusing. So you have 20 times 2 times 2, or this can be written as 20 times 2 squared. 20 times 2 squared. To find the number of bacteria after 3 hours equals initial number times rate of growth equals 20 times 2 times 2 times 2. Therefore, our initial was 20. Each time, 1 hour, 2 hours, 3 hours, we just added an extra 2. So after the 3rd hour, we had our 3 2's. Now if we want to factor this out to simplify it, we see 20 ends in a 0. It's divisible by 5. 5 times 4 times 2 times 2 times 2. 4 is even, so let's make it 5 times 2 times 2 times 2 times 2 times 2. And this gives us 2 to the 5th power times 5. This is how much bacteria there are after 3 hours. I'm going to flip this and try B. B states, Shauna deposits $100 in a bank account that earns 5% interest compounded yearly. How much will be in her bank account at the end of 5 years? Here's our solution. When interest is compounded yearly, a year's interest is deposited in the account at the end of the year. During the next year, interest is earned on this larger balance. Because Shauna's deposit increases to 105 of its value each year, she can use the formula A equals P1 plus RN to find out how much money she has left in her account after N years when she invests the principal of P dollars at an interest rate of R%. So let's substitute the values we know. What do we know? Shauna deposits $100 into a bank account. $100 will be representative of P. Next value that we know is R. R is our interest rate, and the interest rate is 0.05. We know this because it is 5%. To convert percent to decimal, you divide it by 100. Move the decimal place over twice. It is 0.05. And that's how we get R. Let's substitute these in to find A equals 100. 1 plus 0.05 squared. Inside we can simplify 1.05 squared and use a calculator to find the final value. We get 127.63 cents rounded to the nearest hundredth. So Shauna's money will be worth $127.63, and she only started with 100. Not too bad. Go ahead and try guided practice on your own, 13 and 14. When you finish, that's the end of the video, and we will see you in class.